Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we are going to discuss types and sources of error. So in this topic we will describe the two types of error, random and systematic. We will examine a number of sources of error and try to determine whether the impact of those sources is random, systematic, or both. We will discuss how systematic errors are issues that must be dealt with and accounted for at the design phase of the engineering process. You also will understand that over the next balance of the course, actually, we will be looking at mitigating the effects of random errors where possible. All right, to begin, measurements that are being taken, including those from sensors, probes, and other devices, will always be affected by errors. Now, a measurement is a scalar value. Even a position vector or a velocity vector is simply a pair, if you're on the ground, or a triplet, if you're in the air, of scalars. And each one of these entries may be affected by the error. Again, it could also be, instead of an XYZ coordinate, it could also be yaw, pitch, and roll. Now, the effect of these errors generally allow them to be classified as one of two specific types. An error can either be a random error or it can be systematic. A random error is a deviation to either side of the precise measurement. And in general, the errors will cause the reading to deviate around the true value. That is, if you were to focus entirely on the deviations, you will see that they generally tend to have an average value of 0. Now, the size or the magnitude of these deviations are correlated to the precision of the sensor or other device that is making the measurement in question. And of course, the more precise your sensor or other device is, the smaller will be the magnitude of these deviations. Of course, if you have greater precision in your devices, that's going to result not only higher initial costs, but probably it will use more power and higher maintenance costs. Now, fortunately, the spread of such random errors can be described statistically, and we can make use of tools in statistics to compensate for random error. Another way, or the most common way of at least reducing the spread, is to take multiple readings and average them. But of course, an issue with taking multiple readings is that this incurs higher costs. Now, in your course on statistics, you will learn about various statistical distributions that can be used to describe random phenomena or random effects. So, for example, all measurements will be affected by normally distributed errors around a mean value or the expected value. And this is your familiar bell curve from secondary school. This is almost universal in nature, and you can actually demonstrate that the cumulative effect of numerous different influences will on average produce something very close to a normally distributed deviation. However, measurements that are being taken independently relative to a periodic event may actually tend to be uniformly distributed as well. So, for example, If you randomly arrive at a subway stop without checking the schedule or your watch, and the train arrives every 15 minutes, your wait will be uniformly distributed between 0 and 15 minutes. If your server receives approximately n independent client requests per hour, then the time between customers will be 60 divided by n minutes, and the distribution, however, can be described by a Poisson distribution because it's not always going to be exactly 60 over n minutes. Sometimes you have two clients that may arrive almost simultaneously, while at other times you may have a few minutes stretch where no clients arrive. All of this will be described later in your courses on statistics, but all of these can be used to describe potential sources of random error. Interestingly enough, if you take repeated measurements that are uniformly distributed and average them, this actually approaches the aforementioned normal distribution. Similarly, under certain circumstances with enough clients arriving per unit time, a Poisson distribution can also be approximated with the aforementioned normally distributed distribution. Consequently, there are many circumstances, even if the error is not truly normal, it can often be approximated with a normal distribution. And this is something we will use. A systematic error is one that is built into the device that is taking the readings or built into the model. This is essentially one where the deviation is consistent between measurements from the actual true value. So for example, suppose that you have a temperature reading, but there is a heat reflector in close proximity which reflects heat onto that sensor, therefore always making the readings slightly warmer. The problem with a systematic error is that they're difficult to detect statistically. Instead, they are, however, reproducible. And consequently, these can be accounted for in the design. So when you are making your engineering designs, your goal is to account for all possible sources of systematic error. So for example, in your design, you may simply subtract a corrective factor from your measurements, or you may take steps to eliminate the error from the sensor or other device. So this is often described as a bias in the reading. Now over the next few slides, we are going to look at sources of error, and we will describe how the source of error may result in either a systematic error or a random error. And of course, a systematic error is one that should be taken into account during the design, while random errors will be taken into account through appropriate applications of statistical algorithms. So for example, one source of error is the fact that we are using floating point numbers and floating point arithmetic. Now, apart from the initial readings, the least significant bits of a floating point number tend to be randomly distributed. With equal probability, the 52nd bit in the mantissa has an equal chance of being 0 or 1. Actually, the fact that the least significant digits tend to be randomly distributed, while the most significant digits are not randomly distributed on tax returns, is actually one source of detecting fraud. So by looking at all of the numbers that appear in a tax return, looking at the distributions of the least significant digits versus the distributions of the most significant digits, it is often possible to detect fraud because numbers that appear as a result of business transactions tend to be random in the least significant digits in the aggregate. However, if you are explicitly committing fraud, you are likely going to come up with numbers and consequently produce numbers that don't match the same distributions. All right, so many floating point calculations simply result in the introduction of additional random errors, and we will try to mitigate these as much as possible. The serious consequences only begin to start occurring when we are taking similar numbers and taking the difference between them, or we are taking numbers that are significantly different, orders of magnitude different, and adding them together. We've already discussed both of these previously. Now, however, recall that for rounding, when we add two numbers, we may have additional bits. And for rounding to say n decimal digits or n bits, we look at the bits beyond the least significant digit or bit. If the digits beyond the last significant digit are exactly 50000, or the bits beyond the last significant bit is exactly 1000, then we selectively round up or down based on the parity of the last remaining least significant digit, be it a decimal digit or a bit. Now, if this was not done, if we always rounded up or down, this would actually introduce a systematic error into our floating point calculations. Now, you're thinking, wait a second, how often is the digit beyond the last significant decimal digit exactly 5 and everything else is 0? That doesn't appear to be very common. It's not going to happen all that often. However, let's go to binary. Suppose we're adding two numbers m and n that are between 1 and 2, not including 2. In binary, two such numbers will have exactly the same exponent. However, you're also absolutely guaranteed that their sum will be greater than or equal to 2, and so you're guaranteed that their sum will have one additional value in the exponent. So for example, here are two floating point numbers between 1 and 2. Let's add these together, but notice that the last bit may be 0 or 1. When we add these two together, we now have one additional digit of significance. It's now 1, 0 with numbers beyond the decimal point or radix point. That last bit, if both the question marks are 0 or both the question marks are 1, that last bit there will be a 0. However, if one question mark is 0 and the other is 1, the last bit in the sum is going to be 1. So 50% of the time that we are adding two numbers between 1 and 2, we will have to perform a rounding based on the above rule. So it is actually quite common that we will apply this parity rule of either rounding up or down. If we did not, that would introduce a systematic error. Instead, we turn a systematic error into a random error that averages around the expected result. If we always round it up, over numerous millions of computations, our numbers are going to be on average larger than expected. If we always round it down, we're going to have a systematic rounding to a lower than expected value. So this was actually a very deliberate choice on the designers of the IEEE 754 standard. Modeling errors are issues that arise from your failure to correctly model the actual system in preparing your design. Now, modeling errors tend generally to be systematic as there are factors that you have failed to take into account, and consequently, how you respond will be incorrect as your readings are not actually, your interpretation of your readings are not actually representing what's actually going on. Now, when you test or deploy your solution, modeling errors will likely reveal themselves and will generally be reproducible. However, on occasion, modeling errors may actually produce random errors. For example, failing to take into account vibrations and consequently not sufficiently shielding sensors from such vibrations may result in random errors larger than previously expected based on the characteristics of that sensor. The next source of error is environmental error. Nature itself is not a constant, and local turbulence, heat, and other chaotic factors will cause random errors in all readings, period. You cannot eliminate these entirely, and they must ultimately be accounted for. Now, environmental factors that are systematic are actually failures in your model. You failed to take into account, for example, reflections, a local source of heat, or other factors that may affect your readings. Another source of error is drift error. So in some cases, a measurement may drift from the true value. For example, clocks that start synchronized will, over time, drift apart, as you are likely not going to introduce using atomic clocks in all your devices. So most drones, for example, will use a quartz clock. And if you wanted to coordinate 20, 50, or even 100 drones, over time, each of those clocks will be drifting apart from their original true time. Such drifts will result in systematic errors. Now, algorithms exist that allow numerous such devices to periodically synchronize their clocks. And these algorithms still continue to work even if there is a failure in one of the clocks, giving a completely erroneous reading as to what time it currently is. And at the same time, these algorithms also allow for errors in the communications of the current times as the drones are intercommunicating with each other. Now, this is easier if there's a central source that is indicating what the time is. But what happens if these drones are all working as a group independent of a central signal that is specifying what the current time is? Now, the drones must communicate with each other to determine what the best guess is to what the current time actually is based on the fact that all of their clocks are drifting. Similarly, if you have a device that is simply recording the angular velocity, how quickly something is rotating, and simply integrating this to get your change in angle, over time you're going to have a bias in the direction you're pointing, and you will have to correct for this. But these are systematic errors, and these can be dealt with other algorithms or with additional sensor readings. And so any course on real-time embedded systems will look into correcting these systematic drift errors. Another source of error are production errors, and sensors or devices that are purchased will not be perfect. Now, we are assuming that there is quality control, so hopefully there is negligible systematic error. But nevertheless, there still will be random error with each sensor or other device or component that is being produced and used. Now, such errors can be reduced with higher costs by purchasing more consistent or more precise devices, or appropriate algorithms that we will see in this course to mitigate additional randomness. So if you have better algorithms than your competitor, you can use less expensive components, therefore making your device cheaper than that of your components. For example, an inexpensive low-pass filter requires a resistor and a capacitor. Well, if you have these two, each purchased resistor or capacitor has specified resistances and capacitances, but there's always an error of maybe 5% or even 10%. If you want very precise circuit elements, that will cost you more. So having a design that compensates for randomness is a much better approach. Another source of error are calibration errors. Calibration is a process of comparing a device to a standard. Now, failure to correctly adjust the device after calibration may or will, of course, result in a systematic error. Deviations from the standard may be considered to be acceptable or within limits. If not within limits, they may be corrected, but in some cases this too is impossible, especially if the device being calibrated is integrated into some other component, and the alternative is to compensate for this inside the algorithms. So this is again another example of systematic error as opposed to random error, at least in general. As one final example, lag time errors. Some sensors simply take time to adjust before a reading can be made. So consequently, reading such sensors before the lag time has passed is going to result in a locally systematic error. So for example, you're taking a thermometer and reading a temperature of some object. If the ambient temperature where the thermometer is being stored is above that which is being measured, then initially the temperature reading will be too high. And if you do not wait until the thermometer has reached equilibrium, the reading will be too high. The converse is equally true. If the ambient temperature is lower, then any premature reading will also be too low consistently. Devices with inductors or anything else that relies on magnets or the magnetic force also will often take time to adjust to new conditions, or even gyroscopes. Also, a 10-day average of individuals with an illness. Again, there are good reasons for taking 10-day averages, as this eliminates white noise, day-to-day noise. However, if there is a significant upswing or downturn in infections, the 10-day average will take time to respond to such significant changes. And if your response, again, you've written a program to suggest what to do perhaps, the response may be inappropriate if it is simply based on using information about a 10-day average. So let's just quickly recap the effect of different types of error. Returning to our classifications, random errors tend to affect the precision of our measurements. Systematic errors tend to affect the accuracy. So to deal with errors, your design should account for systematic errors, and our algorithms that we will cover in this course will mitigate the effect of random errors. Now, one could devote a single high-precision device that is dedicated to taking one reading continually and then responding appropriately depending on what the value is. But this is actually going to become prohibitively expensive. For example, always watching whether or not a temperature has exceeded a specific value, and as soon as that reading is exceeded, immediately sending an interrupt to deal with it, that's going to be very costly, as that sensor is always on, which means it will wear out sooner, and that's going to use more power as well, so higher maintenance costs, etc. The goal of engineering is to respond economically as well as ensuring that all hard real-time constraints are met. Consequently, sensor readings are made periodically and not continually. The period, as you will learn in your later courses, is chosen to ensure that no hard real-time limits are breached. If, for example, the temperature of a batch of a vaccine cannot exceed some value, then you have to choose your period sufficiently so that it's guaranteed that your response, that is, turning on the cooling device, is soon enough after the reading that it can keep the temperature below that critical temperature. Now, the reason we use periodic sampling is because this is the only approach that can be analyzed mathematically. And you're going to see more of this in your course on linear systems and signals. Another nice feature of using statistical analyses is that you will also be able to use less precise devices. This will lower your startup costs, but it will also lower your maintenance costs and perhaps your power costs. Consequently, regardless of what you are reading, you are going to be periodically sampling a sensor, and those measurements are going to be less than perfectly precise, even if you account for all systematic errors. You now have data that looks like this, and you have to interpret this not with a human being looking at it and observing, oh yes, there tends to be a trend upwards, but instead you must be able to detect and respond to such trends in mathematical algorithms. So in devising numerical algorithms, we have to take into account the random errors that you see in the above periodic readings, and we will take those into account in the future lectures. We will also see how we can deal with them to minimize the effect of the errors, random errors, in such readings, and we will be able to detect that yes, indeed, there seems to be a positive trend in these readings, even if the sensor is not very precise and we have significant random error. After all, GPS is not that accurate. 5-10 meters. Now, more of this is going to be covered in your statistics course and your courses on linear systems. Specifically, there you're going to be looking at something called the Z-transform. Now, one solution, which works under certain circumstances, but unfortunately not always for engineering, is that if you are taking readings of a signal that is known to be constant, or at least approximately constant, and it is only being affected by normally distributed errors that are random, and those errors have mean 0, then the single most efficient means of eliminating that error is to take a running average of the last n samples. And there is no other statistical algorithm that is more suited to eliminating such noise. Problem: this doesn't work very well if the signal is not constant. So even a linearly increasing signal, it would be inappropriate to use this technique. Following this topic, you now understand that there are two types of error, random and systematic. You have also considered various sources of error and describe these sources as having either systematic and or random error. Now, of course, the investigation here is very superficial, so do not take anything in this lecture as gospel. Anytime you are investigating an engineering design you are creating, you must consider all sources of error and determine what the impact will be. You are aware now that systematic errors must be taken into account during the design phase. And you understand that for the balance of this course, we will also be looking at mitigating the effects of random errors, including, but not limited to, random errors introduced by floating point arithmetic. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!